Welcome to the lecture on Introduction to Discrete Compounding and Discrete Payments. So, we discussed about the different types of interest, typically simple interest and compound interest, and based on that you have other terminologies like discount rate or so. Now, when you have the dealing with the investment agencies or the banks or so, we normally come across the loan terms, or when we take something from any bank. So, there you have to deal with these compounding, at different times you have at different time you are going to pay in a different way. So, you have certain factors, they are known as compounding factors, and these factors are basically used to get the future value or current value, or even we will talk about the terms like annuities. So, these needs to be understood to you, and for that we will discuss about the discrete compounding and discrete payments in this lecture. So, first of all we discussed about the cash flow diagrams, that is quite clear to us that in the cash flow diagrams, this is a diagrammatic representation of the cash transactions or the transactions in the terms of receipts and reimbursements at different time steps, discrete time values. So, that is how the cash flow diagram is represented, and you have so this is your present time, and then your time, these compounding periods are defined. So, 1 2 3 4 5 6 like that. So, it will go to n. So, that is your, so where sometimes you may have some flow like this. So, what this kind of transactions we will be talking about the cash flow diagram. So, this diagrammatic representation is known as cash flow diagram. Now, the cash flow, when we talk about, there are different types of cash flows, and the different types of cash flows are like single cash flow. So, single cash flow means you are going to invest something now, and you are you have received something today as a loan, and you have to pay at the end something. So, this is how this is a case of single cash flow, because ultimately you have only one transaction, how much you have to pay maybe after some years. So, when compounding is going on, that is a kind of single cash flow. Then there are also cases of equal or uniform cash flow. Now, this in this cash flow, what happens that many a times what we do is we receive a loan from the bank or the financial institution, and then we are trying to pay it in the equal series manner, even on monthly basis or on an yearly basis. So, such are the examples of equal uniform flows. You have the transactions during the span of the time in a single amount, that is same amount which is going on. So, suppose you have taken from the bank certain amount today, and then every year end or every end of this period, compounding period, you are going to pay some amount to the bank. So, ultimately this amount which you are paying every year, so basically that is known as annuity also. So, this is equal or uniform cash flow, because here it will be something like going on every year end or so. Then there may be cases like linear gradient series. So, the cases may be linear gradient series. Now, what does it mean? Linear gradient series means you have started, you started from 0, 1 2 3 4 5 6 7 or 8 or like that you are going. Now you started paying some amount, you are receiving or paying at this, and then every year you will be having some increase, and increase will be by a fixed quantity. So basically this is the increase, and this increase is fixed. So every year you will have an increase in the amount you are paying. So this gradient is known as the G. So basically it is a linear gradient, because it is a linear profile. So we talk about the linear gradient series. Suppose you are going to deposit 1000 rupees in the year end, then the next year end 1500, after that 2000 or 2000, then 2500 in the next year or low. So in that case it is a case of linear gradient series, and this may happen because someone wants to save his money every year, and since every year he is expected to get some increment. So maybe the increment, from the increment he will be putting towards saving. So suppose he is getting increment of 1000 rupees. So he is increasing his saving every year by 1000 rupees. So something like there will be a base amount, and then this will be the increment every year. So that from the base, in the first year it will be, second year it will be G increased, then it is 2G increased, 3G increased, or like that. So this is a type of linear gradient series, and we may deal with such kind of series where we have to find the ultimate aim will be to calculate the total equivalent value. It may be equivalent to certain uniform flow series. So this gradient series must be represented by one equivalent uniform flow series, or it may have an equivalent future amount or equivalent current amount or so. So this also we will discuss. Then you have geometric gradient series. Now what happens in this geometric gradient series, that here also you are increasing or decreasing. Now in the case of linear gradient series, not necessarily always we are increasing, we can also decrease. So suppose we are giving the 10,000 rupees in the first year, and second year we are giving 9,000, third year we are giving 8,000. So we are increasing 1000 rupees every year. So in that case G becomes negative as minus of 1000. So that way it will be increasing or decreasing series. Now in this case so we are seeing that we are increasing that amount by a certain fixed quantity. Now the same thing may be in terms of increasing or decreasing order, but by a certain percentage. So suppose you are giving you are in the first year and you are giving you are getting something like 100, second year and you will be getting 10% increase, so it will be 110. Then you will have again 10% increase from there, 121, further increase, so it will be 133.1, like that. So further increase 146.41, like that. So it will be 160 points, something like, so it will go on. So such series, they are not basically the linear one, basically they are having some parabolic type of profile, a different profile, not than linear. So this is known as the geometric series, gradient series, and in that basically also again the purpose will be to represent this or to know this, so that you have to ultimately find equivalent to uniform cash flow series, or the future value or the current value of that cash flow. So that will be your geometric gradient series. Then most commonly you will also get irregular series. Now irregular series means along the timeline you do not know when will be what. So there may be some in here, some increase, then further it may go, then come down, then it may be here. So such series are basically they are known as the irregular series. Now in such series you have to if there is a pattern by looking at this, you can use those formulas respective formulas to find the equivalent amount. But otherwise, if there is completely irregular, there is no pattern, in those cases you have to find the equivalent amounts at a particular time, and then ultimately when all the values equivalent of all these transactions are calculated at a particular time, then you can basically come to any other timeline or so. So that way you have the different types of such type of the cash flow series, which is likely to be encountered in our future studies. So we will be talking about the different types of. So basically what happens that we normally deal with the terms known as the factors. So they are so normally what we do is we normally are interested to find some factor which should be multiplied with either the principal value or the future value, and then in that case we intend to get other terms like maybe future value from present value, or maybe annuity value from the present value. So all these things are many times required to be calculated, and that is what we will try to see further, that what are those, how these factors are being named. So what are the name of these different factors that we will see. So among them we will discuss discussing about the single cash flow series. So in that we have the single payment compound amount factor. Now this single payment compound amount factor, this is a factor when you will multiply this with the present value or the current value in other terms, or present value, we will not talk about some terminologies. So you will have P as present value, then we will have F as future value, then you will have I as rate of interest, N is number of terms or years, how many times, so what is the so these are the normally terms which will be required at this stage. We will also come to know about A is annuity value or equal uniform cash amount, so annuity. So this single payment compound factor, this is a factor when multiplied with present value gives you the future value or the compound amount. Basically future value is nothing but the compound amount, because there is compounding going on in during that period. So we know that when we invest any amount P, now it will be P into 1 plus I after 1 year, P into 1 plus I raised to the power 2 after 2 years, P into 1 plus I raised to the power 3 after 3 years. So basically your F becomes P into 1 plus I raised to the power n for the rate of interest I, and n be the number of years. So basically this 1 plus I n raised to the power n, so this 1 plus I raised to the power n is single payment compound amount factor. That is also known as CAF. So that is how this factor. So this factor you can calculate, and when you will study in our later lectures. So when large amount of these values are required to be known, you can even refer a table. That table talks about these values. So now this factor, since it is being multiplied with P, and this gives you f. So, basically they are known as f by p I and n. So, this is this single payment compound amount factor. So, multiplied by p, it will give you the f. So, f by p I n, we can write this basically is the notation, and this is nothing but 1 plus I raised to the power n. So, suppose you are required to tell about the value which will be accumulated after suppose 10 years. So, and you are investing now 15 lakh rupees. So, 15 lakh is to be multiplied with the compound amount factor, that is single payment compound amount factor, and that will be 1 plus I, and rate of interest is suppose 10%. So, 1 plus 1.1 raised to the power so suppose number of years, and that will be the factor multiply with p, simply give you the amount of f. So, this is the single payment compound amount factor. Now, similar to that you have, so opposite to it or reciprocal of it will be single payment present worth factor. So, this factor is basically represented present. So, you have to find p and given f. So, this factor is represented by this symbol p by f I n, means this factor when multiplied with future amount gives you the present amount or principal sum. It means the factor is to be calculated, and this when multiplied with f will give you p. So, we know that p will be f into 1 plus I raised to the power minus n, or f divided by 1 plus I raised to the power n. So, basically this factor 1 plus I raised to the power minus n, this becomes single payment present worth factor, and we also call it as we calculate, we find p given f. So, p by f I n. So, it was f by p I n, and this is p by f I n, and this is 1 plus I raised to the power minus n. So, that is how you calculate these single payment compound of amount factor or single payment present worth factor. So, and you calculate all these values. Now, we will further discuss about the other series, which is the uniform cash flow series. And when we talk about the uniform cash flow series, we talk about the payment which is made every year end, and that amount is constant. So, how to find such cases? So, basically these amount which is made at the year end or whatever you receive at the year end, they are known as annuities, and based on that you have a series known as equal payment series compound amount factor. Now, this factor basically is in this case you find f, this is future amount, compounded amount, provided A is given, every year end what you are getting that is given, and based on the rate of interest and the number of times the compounding is taking place or years. So, you can see by looking at the cash flow diagram, basically it is nothing but every year end you are giving, and it will be n minus 1 and this is n. So, every year end you are depositing certain amount, that is basically fixed amount. So, it is all is A, and ultimately this here also you are giving A, and here also you are giving A, and ultimately you will get one amount, that is your future amount, that is F. So, that is what is the example of you know the equal payment series compound amount factor. So, this factor when multiplied with equal annual amount gives future value or compound amount. You know, so certainly the rate of interest and this is known. So, if you look at this series, what we see is that we have A going on here, then A is going you know every year. Now, what you see is that if you try to see its value, this A which is given at the end of n years, this A is as usual, it is not getting any interest. So, if you see end of period payment, and its contribution at n. So, end of period payment, you know 1, 2, 3 to n, basically we are you know paying. Now, you know end of period payment. So, end of period and this is payment. So, end of payment is anyway we are paying only A. Now, its contribution at n is how much? So, this A which is being paid here, its contribution at this point is only A, because it is not getting any time to you know compound. So, its value will be only A. Now, this point at n minus 1 it is getting you know one compounding period. So, it will be getting, so if it is n minus 1, it will be getting A into 1 plus I. So, you know this way it is going on, and ultimately what we see at the first time, and this is your you know nth time. So, this way you will have for n minus 1 it is 1 plus I only. So, for the first one it will be coming as 1 plus I raised to the power n minus 1. So, if you look at this and this sum, so if you sum them, so that way your its value will be you know calculated for you know every you know value. So, what we see is for the first case is nothing but n minus 1. So, that is why it will be you know A into 1 plus I raised to the power n minus 1. So, this is nothing but n minus 1. So, it is power 1. So, n minus so that way it will have you know 1 plus I raised to the power minus 1. Here this is coming power 1. So, this is nothing but this is corresponding to n minus 1 is 1. So, this 1 is going here. So, this way for n minus 2 it will be again A, and it will be A into 1 plus I raised to the power 2. This 2 comes from n minus 2. So, this 1 it will be n minus 1 is 1. So, it will be n 1 plus I raised to the power n minus 1. So, altogether all its sum, this summation should be equal to F. Its summation must be the same F. So, what we see is F will be A plus A into 1 plus I plus going on up to A into 1 plus I raised to the power n minus 1. So, altogether there are n terms, and that is why it will be it is a basically series of the geometric series where the first term is A and common ratio is 1 plus I. So, A into and term is total term is n. So, 1 plus I raised to the power n minus 1 and divided by r minus 1, that is 1 plus I minus 1. So, it will be a into 1 plus I raised to the power n minus 1 divided by I. This is the expression which basically equates the f value in terms of a, I and n, and this factor. So, what we see is this factor. So, factor is basically 1 plus I raised to the power n minus 1 by I. Now, this factor when multiplied with a, this will give you the f. So, that is why this factor is basically known as the equal payment series compound amount factor, and that is why we call it as, since we are calculating f based on I for a particular I and n. So, this is represented by the factor f by a I n. So, you will have a table, and whenever you have certain a, then for some periods it is being accumulated, so that n if you know, and rate of interest you know, and according to that, as per the table you can just calculate these values and calculate ultimately the f value. So, that way we find and we give the name to these factors. Now, on the contrary, you may be required to find the a when f is given. So, that factor is known as basically equal payment series sinking fund factor. Now, what we see here is that in this case this factor, you have a fund which is getting sunk, and basically you want to find, so you want to find a. So, the factor multiplied with future value will give a. So, basically it is like you have a future, in future you have certain amount which is there supposed to be deposited, and how much you will be drawing every year equally, so that the equivalent amount ultimately it replenishes. So, it is gone. So, for that this factor is, so that factor is basically you have to find a provided f for I and n, and it is basically the reciprocal of the f by a I n. So, this factor will be 1 by f by a I n, that is equal payment series compound amount factor, and in that case we have calculated. So, it will be I upon 1 plus I raised to the power n minus 1. So, you may be told that this amount will be there deposited at the end of so, and what should be basically the every year amount which can be taken out, so that in the end it becomes 0. So, that way you have equal payment series sinking fund factor which is defined, and that is your I upon 1 plus I raised to the power n. So, you can have different type of questions. We will have it when we will deal with the question solving session, and we will see that how these factors are utilized to calculate the values of the f or a or p or f or so. So, we will have other more factors in our coming lectures. Thank you very much.